In this video, we will discuss the transient analysis. So the transient analysis is used to find the response of a signal with respect to time, how the system or the circuit behaves with the signal with respect to time. So we will explain the transient analysis and we will do some examples and we will see what are the options available in the transient analysis. So let's do initially make a schematic with the transient analysis. Okay, so in the transient analysis we have a lot of options available. Even for the sources, we can have a DC source, we can have a sine wave, square wave, pulse, anything we can have in the transient response which is varying with time. So in the transient analysis, if we plot a graph, the x-axis will be time always. So transient analysis is used to find the system response with respect to time. So let's begin with the sine wave or square. I'm placing a analog library, sources. I want, okay, we start with DC voltage, VDC. We know the DC voltage is fixed with respect to time, there will not be any change. But let's illustrate that also. 5 volt is a DC voltage and I want ground also before doing anything. So I place the ground and give 5 volt there, 5 volt for the sources. So just with this, let's do and see the waveform. So go to analysis. Here you can see the tran stands for the transient. So it's stop time is asking. So that means how much time we want to carry out the analysis. For the time being, I am giving as 100 microsecond. So it will start from 0 and up to 100 microsecond it will simulate. And I want to plot the output to be plotted. I didn't name this, I didn't label this node. I'm just plotting that node and run the simulation. So our source is a DC source and there will not be any change with respect to time. So that is from 0 to 100 microsecond it's simulated and the source was always 5 volt. Now let's change the source from a DC to sine. So there are a lot of options available here: DC voltage, delay, offset, amplitude and those things. I'm using the amplitude as 1 volt and the frequency I'm using 100 kilohertz. Save and plot the signal. So here I am expecting it is the sine wave. So it is starting from 0. We give the amplitude 1 volt. So it started from 0 and it went to 1 volt and it is the sine wave. And the x-axis is the time and y-axis is the voltage sine wave. So now I can introduce a DC value. So it was amplitude we give 1 volt, so it started from 0. I'll show you once again. It started from 0, it went to 1 volt, and again it came to minus 1 volt. So if you want a DC shift, I can give a DC value to the sine wave. If I give a 2 volt DC, then it will oscillate on the 2 volt. Let's run the simulation. See, now it started, instead of 0, it started from 2 and it went to 3 and it came to 1 volt. Another example is the pulse train, that is V pulse. So the V pulse, no need to put DC voltage. So voltage 1, let it be 0, voltage 2, I want 5 volt, and the period I want 10 microsecond. We can give delay time. Okay, rise time I am using 1 microsecond, fall time I am using same 1 microsecond, and pulse width 5 microsecond. Let's simulate and plot this source. See here, you can see you give a 1 microsecond rise time and a 5 microsecond pulse width, again 1 microsecond fall time. Now in the go back to the sine wave. We sine, our amplitude was 1 volt and frequency 100 kilohertz. I want to explain one property of the transient analysis. So that is you can see in the transient we have accuracy defaults. It can be liberal, moderate, or conservative. Okay, you select the liberal and run the simulation. And now with that, select conservative and run the simulation. See, did you observe any difference in that? Okay, the difference is for the liberal analysis, the simulator will calculate this point, this point, this point, this point, this point, this point, and it will draw a line which is connecting all these points. In the liberal, the number of these points in a particular width from here to here, the number of points will be less. In the moderate, there will be more number of points, so that the curve will be more accurate. For the conservative, you will have 1 point here, again 1 here, 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 here. In these two values, in these 2 points itself, you will have a lot of points, and when you connect all them, you will get a perfect sine wave. You can observe that in the simulation itself. I increase the frequency to 1 megahertz. Okay, and I run the simulation. First, initially I will run with liberal, so there will be less number of points, and you can see I'm zooming the graph, and you can see it is kind of lines. Instead of a pure sine wave, you can see lines here. You can see 1 point here, then 1 point here, 1 point here, 1 point, and I just connected these points. Here it is very clear. Here you have 1 point here, and 1 point here, and 1 point here. So If you use the liberal, the number of points to be calculated will be less, but the accuracy will be less. So what is the advantage of liberal analysis? Since the number of points is less, it will be very fast. Suppose you have a huge circuit. If you are running with liberal, the circuit will be very fast. You can get the output very quickly, but it will not be very accurate. But if you use the conservative, it will take lot of time to simulate, and it will calculate each and every point in the graph, so that your output will be very accurate, and the moderate is in between that. So now you select the conservative and run the same simulation. You zoom it. See, now you cannot see that type of points. It is almost a sine wave. It is almost a sine wave, and it is more accurate. But in a small simulation, it doesn't make much difference, because it will not take much time difference in between these two, as we saw. But if your system is very large and you have a big circuit, then running the conservative will take long time compared to liberal. But the accuracy will be good for the conservative, and it's moderate and liberal, and for the liberal the accuracy will be less, and the moderate, the speed and the accuracy will be moderate. So this is one very important point in the transient analysis. Okay, and let's do one example of a filter. Let's do an RC filter, a low pass filter. I need a resistor. I am using the value 10k. And I rotated that and I placed it here. Press F, and I need a capacitor, and I used 1 microfarad. Copy this ground from here. So now this is a low pass filter. Let's run the transient analysis. Okay, I want to plot the output also. So first of all, you label the output and input. So this is my output and this is my input. I want to plot. Now I am deleting this. I want to plot plotted in and out. You can see the output is almost 0 and the input is a sine wave, pure sine wave. So the low pass filter is filtering your sine wave completely. So if you want to get some output, you can see how much is the if you zoom, I separated the window and I zoomed it. Now you can see the input amplitude is 1 volt and the output amplitude is very less. It is in microvolt only. It is because of your higher frequency. If you decrease the frequency, instead of 1 megahertz, suppose I used 1 kilohertz. Okay, the time is too small, so I increase the transient time into 1 second. Okay. Now you can see there is an improvement in the output. It is not in microvolt now, it is in millivolt now. If you press F, fit to screen, you can see both are sine waves, but it is in 10 millivolt only. So if you reduce the capacitance value, suppose instead of micro, if I am using the nano, then I will allow, see, if the capacitance is nano, you can see both are of the same amplitude. I have both input and output here, they are of the same magnitude. That means now filtering is not happening. Almost all the output is going through all the input is going through the output. If you separate this window, now you can see two waveform of almost equal amplitude. Input is in 990, it is near to 1 volt, and the output is also 1 volt. If you use something in between, suppose I used hundreds of nano, and run the simulation. Now you can see our output is very much not very much attenuated, but attenuated. This is the response of this filter to the sine wave. So let us do the same filter. What is the response to a pulse wave? So I am using a pulse. Voltage 1 is 0, 2 is 5. Period I want 100 milli. Rise time, fall time I am not giving anything, so it will take the default value around 10% or something. So now I can see the input and output. So the input is varying very quickly, but the output is not varying that much because of the presence of the capacitor. So it will take little bit time to follow the output. If you increase the frequency, this will be more evident. To increase the frequency, I decrease the time period to 10 millisecond and run the simulation. So if you zoom, you see the square is now almost, you can call it as a triangular wave, because input is changing very quickly. Output will take some time to reach to this point, and again for the falling and rising also. So there is a huge rise time and fall time for the system. In the transient response, I explained what is the conservative, moderate and liberal. So I told you it will not be significant for you if your system is not big. But if your system is big, if you are doing the conservative, it will take long time to finish the simulation, and it will take a huge amount of memory also. Memory means there will be a lot of file size will be there. So if you want to reduce the file size and make the simulation quick, simulation faster, you can use the liberal. One more problem, if you can go to output and you can click the save all. So by default, all public node will be saved in voltage. So if your circuit is small, it will not create any problem. But if your circuit is big, then saving all the node voltage will consume a lot of space in your hard disk. So if your circuit is big, there is no need to save all the nodes. If you want, you can save, but you can give selected. If you give it as selected, you will save only the nodes which is selected here. All the nodes will not be saved. Okay, this tip you can use if your circuit is big and your space is limited. But if you have a huge space and your circuit is small, then there is nothing to worry. You can do whatever you want. So it is not a problem. Let's consider this example. I have an inductor here with 1 microhenry, and I have a capacitor with 10 microfarad and one resistor with 100 milliohms. So this is the resistance of the inductor as an RLC circuit. And input, I am using a step wave from 0 to 5, and let's plot it's a step response we are analyzing. So you can see the input is a red signal, and so it is going from 0 to 5 volt very quickly. But because of the property of the inductor and capacitor, it is taking some time to settle to the final value. So this is very much depend on this resistor value. If I decrease the resistor further, suppose I decrease the resistor to 10 milli, then it will take more time to settle into the final value. You see, the amplitude is decreasing, it will settle finally, but I am running only up to 200 microsecond. That's why I cannot see where it is settling. But if I increase the capacitor, increase the resistance, so there will be more damping. Suppose I increase this to 200 milliohms, there will be more damping and the system will settle very quickly. You see, there is only 1-2 oscillation. After that it is settling. And if I increase this value very much to, you say, 500, or suppose I put 800, so it will be kind of damped response, over damped response. There will not be any peak. It will just smoothly follow the input. So here you can find the rise time and those things. So this type of analysis we can use with the transient analysis. So before stopping this, I will do one more typical example, that is the transient response of an inverter. So I am removing all these, delete all this, and I just make an inverter. So I want EMC library and MOSFET. I want 1 NMOS. Okay, minimum size NMOS I can use, no issue. And I need a PMOS also. For the inverter, generally we use PMOS size, double the size of the inverter to get equal rise time and fall time. Body is connected to the ground. Here the body is connected to VDD, and I need a VDD here. This will be the input. So input we need only up to 1.8 volt. Period I need 50 microsecond is fine. No delay I need. Rise time, fall time, and those things I am not giving. It will take by default it will take duty ratio 50%. So in the input, this is the input, and I need an output also. Okay, I need a supply voltage, that is VDD. I am changing this V pulse to VDC, and this is I am using the supply. This voltage is I am using as supply voltage, so I give this to the inverter supply. So this is the output node. Label it as out, hide, Okay, let's run the simulation. So you can see the red one is the input and this is the output. When the input is at 1.8 volt, output is at 0, and when the output is at 0, when the input is at 0, output is 1.8. And you can see the rise time and fall time also. If you want to see this very clearly, what you can do is reduce the rise time and fall time. If it is suppose you put the rise time very small, 10 nanosecond, and fall time also you put 10 nanosecond. Now you run the simulation. Okay, let's increase the frequency. So the period I used only 5 microsecond, and let's run the simulation. Here you can see there is a little bit delay in between the input and output, and there is a finite fall time. It is taking from here to reach from 1.8 to 0. It is taking some considerable amount of time, and in the here also there's a little bit delay. It started from 0. After sometimes the input started from 0, it is falling, and there's a considerable amount of fall time and rise time you can observe. So I'm stopping the tutorial here. The intention was to show some features in the transient response. It's a very simple and very familiar analysis.